physics problem. So I made this problem up, and I didn't work it out yet, so it might be a disaster, but let's just get to it. Here I have a metal bar, and there's a current I. That didn't really show up. And yes, I made these diagrams in Web v Python because it's easier to draw that way. And that's X, Y, and Z direction, and so forth. So we have a 1.5 volt potential across the bar, and it has an electron current, and the current carriers are electrons. E is 1.6 times 10 to the negative 19th coulombs. Mobile charge carrier density, N, is 2 times 10 to the 28th electrons per cubic meter. The bar has a resistance of 3 ohms, and it's in a region with a magnetic field B. The magnitude is 1.3 Tesla. That's what we got. And then we got the dimensions of the bar and everything like that. So let's just jump right into this. Number one, what is the vector value of the electric field in the direction of the length of the bar? Okay, so we got a couple ways to do this. I'm going to first solve for the current I. But you actually no, I'm not going to do that. I'm going to use, there's two, and I hope my numbers don't conflict. But let's do this. A. Let's call this E parallel, right? Because if you think about it, here's my bar, like this. There's going to be an electric field going this way, which makes the charges move. But then the magnetic field is going to make an electric field, it's either this way or that way. So we'll call that E perpendicular, and we'll call that E parallel. All right, so there's two electric fields. One makes a current, one makes a charge separation. That bothers me right there. Okay. So what is that? Well, if I look at the bar from the side, I know delta V is 1.5 volts. I also know the length, L, is 0.01 meters. So if we assume a constant electric field, and we know the current's going this way, so the electric field is going to be that way, then we can find the magnitude, E parallel, is just going to be delta V over L. It's actually negative that, but we're going to do the direction anyway. Delta V over L. So that's going to be 1.5 volts divided by 0.01 meter, which is 150 volts per meter. So E parallel, and you'll notice right here, that's the positive x direction, so the electric field's in the negative x direction. We can write it as the following: negative 150, 0, volts per meter. Wasn't that fun? Now, the other way, you could say I equals delta V over R. That's Ohm's law. And then I know R is equal to 3 ohms. Delta V is 1.5. And then I can say I is E N A U E. So that's, now the problem is I don't have, this is the charge carrier density, the area which I can get. I know the size, but I don't know this. So let's just leave that off. I never put the electron mobility. I should add that to the problem though. I'll add that to the problem. I'll find out the correct value and I'll add that in there. And I'll copy that problem in the description down below. Okay, let's move on to question B. What is the drift velocity of the charge carriers? Okay, so now I do need this, right? I can use this to find the drift velocity. So let's get a new piece of paper. No point scrunching it up. So B, I equals E N A V D. So this is the relationship between the electric current in amps, the charge carrier density, the cross-sectional area, and the drift velocity. So I can solve for the drift velocity. The drift velocity is going to be I divided by E, the charge of an electron, in A. Now I do need to calculate A, and I need to calculate I, which I just did over there. It's 1.5 volts divided by 3 ohms, which I can actually do in my head, 0.5 amps. See, I didn't even need the calculator. Now, for the cross-sectional area, here's where this nice picture comes in. It's 0.05 by 0.005 by 0.001. So this is 0.001 meters times 0.005 meters. So that's going to be, I can do that. A equals 1, 2, 3, 10 to the negative 6. So it's 5 times 10 to the negative 6 meters squared. And I know E, 1.6 times 10 to the negative 19th. I know N, it was from before. It was 2 times 10 to the 28th. And then there's A and V. Okay, so let's solve for VD. VD equals the current, 0.5. I'm going to leave off the units, divided by 1.6 times 10 to the negative 19th times 2 times 10 to the 28th times 5 times 10 to the negative 6. And I can't do that in my head. But I do have a calculator. You could use Python. You should use the calculator that makes you happy. I like this RPN calculator right here. So let's put this in. 0.5, enter. 1.6 times 10 to the negative. There's a negative sign. It's not negative. I feel dumb. Nope. Times 10. Oh, there it is. Negative 19 divided by 2 times 10 to the 28th divided by 5 times 10 to the negative 6 divided by. And I get 3.13 times 10 to the 5, negative 5. There you go. Drift velocity. Moving right along here. And you know, there is a reason we found that. Because C, what is the vector value of the electric field perpendicular to the current due to the magnetic force? So let's just draw this picture, another picture. So I have these negative electrons, and they're moving this way. So that's V. But QV is this way. And then I have a magnetic field into the board, into the paper. And they're perpendicular. F is going to be QV cross B. So that's the magnetic force. So what direction is the magnetic force in there? Well, QV is this way. B is that way. So I'm going to pick, there's two possible choices. It could be up or down. Okay, and I can pick that by saying QV cross B. If I take my right hand and I cross through QV, which is that way, and then B, I get this way. FB. So I'm going to get negative charges up here and positive charges down here. So I really answered these questions backwards. Now those charges will continue to accumulate and create an electric field this way until the electric force on this charge, so here's QV, here's FB, here's FE. So these two forces are going to be the same, and FE is Q times E. So we don't have to use vectors here because everything's in opposite directions. So I can write this, the magnitude FB, as QVB, and that's going to be equal to the magnitude of this, which is QE. So now I can solve for E pretty easily, right? The charge cancels. I know V, so E is V times B. So let's put in our values. I had 3.13 times 10 to the negative 5th. Yep. Meters per second times the magnetic field of 1.3 Tesla. So let's put that in. Drop. 3.13 times 10 to the negative 5th, enter, 1.3 times. I get 4.07 times 10 to the negative 5 volts per meter. And the question said, what's the vector value? So I need to write this as E equals 0, 4.07 times 10 to the negative fifth, 0 volts per meter. Done. Sketch the charge distribution. I did that already. And you'll notice here, if I had positive charges moving, this is the great thing about the Hall effect. If I had positive charges moving, QV is going to be the same way, but that force is going to be up, and I'm going to get positive charges up here, right? And the electric field, this is E perpendicular, will be down. So you can't tell the difference between positive and negative moving charges. What is the change in electric potential across the height of the bar? So this. What's delta VH? What's the delta V that way? Well, if I just want the magnitude, it doesn't really matter, but we can do it either way, right? Because now I have a constant electric field and I know the width, the height. So delta V is just going to be, the magnitude is just E perpendicular times that height. And so we know the height, the width. I want the change in potential across the height. I did say height. Okay, that's fine. E perpendicular height. It's going to be 4.07 times 10 to the negative fifth times the height, 0.005 meters. Plug it in the calculator. Drop. And I dropped the answer. You know that. 4.07 times 10 to the negative 5. Enter 0.005 times. And I get a tiny voltage of 2.03 times 10 to the, oh my gosh. There's a way to convert this into scientific, but I can't remember. 1, 2, 3, 4, 5, 6, 7, 10 to the negative 7 volts. So it's a super tiny voltage difference, but this is how the Hall effect sensor works, right? If I measure that sideways voltage, I can use that to calculate the value of the magnetic field passing through that. So that's how those work. That's how your phone determines the direction. It has a Hall effect sensor. It actually has 3-dimensional Hall effect sensors. But there you go. That was it. The end.